Chapter 5, Module 5, Path Homotopy. This module builds the basics for construction of fundamental group of topological spaces. Looking at a topological space X, we intend to designate a collection of objects and define a composition on that collection such that it forms a group. Keeping that in mind, we define a path and product of paths. We start with defining a path. Suppose X is a topological space, x0 and x1 are 2 points in the topological space X. Any continuous function alpha from the closed interval 0 1 to x is called a path joining x0 and x1 if alpha 0 has the value x0 and alpha 1 has the value x1. The points x0 and x1 are respectively called the initial and the terminal points of the path alpha. In case the initial and terminal points coincide, that is x0 and x1 at the same point, then the path alpha is called a loop based at x0. In what follows, we always mean a topological space when we write capital X, and x0, x1, x2, they are the members of the space X unless stated otherwise. Now, product of paths gives a method of joining one path with the other. We define the product this way, that suppose alpha is a path joining x0 and x1 and beta is another path joining x1 and x2. Then alpha star beta defined below is a path joining x0 and x2 given by alpha star beta at the point t is alpha to t when t is between 0 and half and beta to t minus 1 when t is between half and 1. That means, when alpha star beta is constructed, in the first half of the interval 0 1, that is between 0 and half, it follows the rule of alpha, and in the second half, that is from half to 1, it follows the rule beta. It may be observed that two paths alpha and beta are compatible for product if the terminal point of alpha coincides with the initial point of beta. For alpha star beta and beta star alpha both to be defined, one needs alpha 0 is equal to x0 and that should coincide with beta of 1, and x1 should be equal to alpha 1 and that should coincide with beta 0. Even if both alpha star beta and beta star alpha are defined, in general the product may not be the same. So, we prove it, or we just look at what is alpha star beta and beta star alpha, then we can easily see that they are not in general same. The product of paths is not commutative, because if I take at the point t equal to 1/4, alpha star beta 1/4 is equal to alpha half, and if I take t equal to 1/4 and put it in beta star alpha, then we get beta star alpha 1/4 is equal to beta half. Of course, alpha half and beta half may not be the same. Also, generally the product of paths is not associative. Now, for associativity of product, we need 3 paths alpha, beta and gamma, and they must be compatible for the product. That means, the end point of alpha or the terminal point of alpha should be the initial point of beta, and the terminal point of beta should be the initial point of gamma. So, when it is alpha star beta and then star gamma, then of course the interval 0 to 1 is broken up into two parts, 0 to half and half to 1. In the first half, 0 to half, it should obey the rule of alpha star beta, and in the second half, that is between half and 1, it should obey the rule of gamma. So, we get ultimately this description of alpha star beta star gamma as alpha 4s when s lies between 0 and 1/4, beta 4s minus 1 when s lies between 1/4 and half, and gamma 2s minus 1 when s lies between half and 1. On the other hand, if we want to find what is alpha star beta star gamma, then the interval 0 1 is broken up into two parts, 0 to half and half to 1. In the first half, it should obey the rule of alpha, and in the second half, that is from half to 1, it should move as beta star gamma. So, we get the description of alpha star beta star gamma as alpha 2s when s lies between 0 and half, beta 4s minus 2 when s lies between half and 3/4, and gamma 4s minus 3 when s lies between 3/4 and 1. For defining a composition on this collection of paths, any two paths needs to be compatible for product. This requirement drives us to take the collection as the collection of all loops, but even then this product is not associative. So, our feeling is that the product as it is will not serve our purpose. So, this leads us to define what is called path homotopy. We now define path homotopy. Suppose alpha and beta are two paths in a topological space X joining the points x0 and x1. If there exists a continuous function capital H from the closed interval 0 1 cross closed interval 0 1 to x such that h s0 is alpha s, h s1 is beta s, h 0 t is equal to both alpha 0 beta 0 and that is equal to x 0, and h 1 t is equal to alpha 1 beta 1 and that is equal to x 1. Then alpha is said to be path homotopic to beta denoted by alpha, this symbol beta. This is, we say, homotopic with respect to or with relative to the points x0 and x1. We shall use a simplified notation that alpha homotopic to beta without mentioning the initial and the final point x0 and x1 in the subsequent development of this course. Now, in this case capital H is called a path homotopy. It is to be noted that H of this above definition is actually a special case of homotopy relative to the points 0 and 1. For three compatible paths alpha, beta and gamma, we have already seen that alpha star beta star gamma and alpha star beta star gamma are certainly not equal in general. The following theorem guarantees that they are path homotopy. So, we state a theorem that suppose we have three paths alpha, beta and gamma in a topological space which are compatible for taking product. That means, the initial point of alpha is x0, final point of alpha is x1 which coincides with the initial point of beta, and the final point of beta is x2 which coincides with the initial point of gamma, and x3 is the final point of gamma. Then we claim that alpha star beta star gamma and alpha star beta star gamma, these two are path homotopic. We now prove this result. The descriptions of the paths alpha star beta star gamma and alpha star beta star gamma are as follows. We have already seen these descriptions before. Now, schematically, the closed interval 0 1 is now broken up into 3 parts, 0 to 1/4, 1/4 to half and half to 1. In the first part 0 to 1/4, it follows like alpha, from 1/4 to half it follows like beta, and from half to 1 it follows like gamma. On the other hand, when we are taking alpha star beta star gamma, we have the diagram as the closed interval 0 1 is broken up into 3 portions, but now the portions are 0 to half, half to 3/4 and 3/4 to 1. First part is followed by alpha, second part half to 3/4 is obeyed by the rule beta, and in the third portion 3/4 to 1 is by gamma. For constructing a path homotopy, we consider this rectangle. Now, if I take the horizontal line on the bottom as t equal to 0 and we take the horizontal line on the top as t equal to 1 and take the other coordinate as the coordinate s, then what we get is the line L1, L2, L3 and L4 will have these equations. Now, we see what we are doing is that the line in the bottom is actually the interval 0 1 broken into 3 portions, 0 to 1/4, 1/4 to half and half to 1, and line in the top, that is t equal to 1, the portions are 0 to half, half to 3/4 and 3/4 to 1. So, what we are doing is we are finding out the equations of the lines L1, L2 and L3 and L4. Now, how do I construct the homotopy? In the first region bounded by the lines t equal to 0, t equal to 1, L1 and L2, that is the region all the points st such that s lies between 0 and t plus 1 by 4 and t varies over 0 to 1. We should give one description of a continuous function, and what we feel that in the first region it should follow as the rule of alpha. In the second region, that is the region bounded by the lines t equal to 0, t equal to 1, L2 and L3, that is the region of all points s comma t such that t plus 1 by 4 less than equal to s less than equal to t plus 2 by 4 and t lies between 0 and 1. In this region, the continuous function should be taken as beta, and in the third region, that is the region bounded by the lines t equal to 0, t equal to 1, L3 and L4, that is the region of all points st such that s lies between t plus 2 by 4 and 1 and t varies between 0 and 1, and in this region it should be the gamma function. Now, by taking that HST is equal to alpha of certain variable where s and t lying in the region of the first portion, second portion is covered by beta and the third portion is covered by gamma. Now, of course, if we check from the initial and final points of alpha, beta and gamma, we can see that these functions are actually continuous on the boundaries. That means, if I put s equal to t plus 1 by 4 in the first equation, then the value of alpha for t plus 1 by 4 by t plus 1, that is alpha 1, will coincide with beta 4 into t plus 1 by 4 minus 1 minus t, that is beta 0, and for the other parts. So, that means using testing lemma we have h is continuous. And of course, if h is continuous function, it can be checked that it is actually a path homotopy between alpha star beta star gamma and alpha star beta star gamma. So, as a special case of this theorem, we get that if alpha, beta, gamma are taken as loops based at some point x 0, then these two functions, these two products alpha star beta star gamma and alpha star beta star gamma, they are path homotopic relative to the base point x 0. Next is another useful result, that suppose alpha and alpha 1 be two homotopic paths joining the points x 0 with x 1, and beta 1 are two homotopic paths joining x 1 with x 2. Then alpha star beta is path homotopic to alpha 1 star beta 1. So, you want to prove that result. Suppose it is given that alpha and alpha 1 are homotopic. So, suppose the homotopy is H 1, and it is given that beta and beta 1 are homotopic, and suppose that homotopy is H 2. Now, by the definition of path homotopy, we get H 1 S 0 is alpha s, H 1 S 1 is alpha 1 s, H 1 0 t is x 0, H 1 1 t is x 1, and by the definition of path homotopy H 2, we have H 2 S 0 is beta s, H 2 S 1 is beta 1 s, H 2 0 t is x 1 and H 2 1 t is x 2. So, now we define capital H by breaking the interval 0 1 into two halves, 0 to half and half to 1. In the first half, when s varies between 0 to half and t is between 0 and 1, we take the function, the description as h 1. And in the second half, that is when s varies from half to 1 and t is between 0 and 1, we take the description as h 2 and paste these two continuous functions to get a continuous function capital H by pasting lemma. Now, of course, if we put t equal to 0, then we have h s 0 equal to alpha star beta s, and h s 1 is equal to alpha 1 star beta 1 s, and h s 0 t is x 0 while h 1 t is 1, which imply that H is a path homotopy between alpha star beta and alpha 1 star beta 1. Now, as a corollary to this result, we may have this, that alpha and alpha 1 are two homotopic paths joining x0 and x1, and beta be any path joining x1 and x2, then alpha star beta is path homotopic to alpha 1 star beta. Of course, this corollary is immediate from the fact that beta and beta itself is homotopic. That means, beta is homotopic to beta by reflexive relation of homotopy. And applying the theorem, we get alpha star beta is path homotopic to alpha 1 star beta. Now, as a special case of this theorem, we obtain another theorem, the same thing for loops. So, if we restate it in terms of loops, then we have alpha, alpha 1, beta, beta 1 are loops based at x0, such that alpha is path homotopic to alpha 1 and beta is path homotopic to beta 1, then alpha star beta is path homotopic to alpha 1 star beta 1. Now, we define a path which traces back alpha. What do we mean by that? Is suppose alpha is a path from the closed interval 0 1 to x, which starts from x0 and ends at x1. Then we want to define a path which starts at x1 and ends at x0. So, we define alpha inverse as alpha inverse t is equal to alpha of 1 minus t. Here if we put t equal to 0, we get alpha inverse 0 is equal to alpha 1, that is x1, and if we put t equal to 1, then we get alpha inverse 1 as alpha of 0, which is x0. So, alpha inverse is just a path which is in the reverse direction of alpha, and we call it the inverse of alpha. Another thing is that for any x, we define a constant function Cx from the closed interval 0 1 to x, which is defined by Cx t is equal to x for all t belonging to the closed interval 0 1. This is called a constant loop at x. Now, suppose alpha is a path joining x0 and x1 in a space x, then alpha star Cx1 is a path which starts at x0 and ends at x1. We see that alpha is starting at x0 and ends at x1, while Cx1 starts at x1 and ends at x1. So, alpha star Cx1 is well defined. It can be proved that alpha star Cx1 is path homotopic to alpha. On the other hand, if we multiply Cx0 from the left of alpha, that means we take the product as Cx0 star alpha, then that is also well defined, and it can be checked that it is path homotopic to alpha. Now, alpha star alpha inverse is also path homotopic to Cx0. Now, if we can see that alpha starts at x0, ends at x1. Now, alpha inverse starts at x1 and ends at x0. So, ultimately we are getting a loop based at x0 when we are taking alpha star alpha inverse. So, alpha star alpha inverse is a loop based at x0, while Cx0 is a loop based at x0. We claim that alpha star alpha inverse is path homotopic to Cx0. Similarly, alpha inverse star alpha is path homotopic to Cx1. Now, it is important to note that path homotopy is an equivalence relation on the collection of all loops based at some point x0. This is a consequence of the fact that the relation of being homotopic to is an equivalence relation, and path homotopy is a special case of homotopy relative to a set. In view of this remark, for each x0, if we take the collection of all loops based at x0 as the collection P, then this P is partitioned into the disjoint equivalence classes determined by the relation alpha path homotopic to beta. Now, we denote the collection of all these equivalence classes corresponding to each alpha belonging to P as the collection pi 1 x comma x0. So, what we have seen is that if we take the collection of all loops based at some point of the topological space X, then path homotopy partitions the set into disjoint equivalence classes. The product of paths naturally defines a composition on this collection of objects. Now, the properties of path homotopy in connection with product of paths drives us to expect that such a composition will give a group structure on the collection of equivalence classes.